Okay, so we were looking at Hubble's law and using it to measure distances to galaxies. So I asked you about the distance to the galaxy we saw earlier with a redshift of Z of 0.37. So just rearrange Hubble's law to make distance the subject. We're given the redshift rather than the recession velocity, so just replace velocity with c times z. And as I mentioned before, then keeping things in the units of the Hubble constant is normally in as a good idea here. So if you here I've put the speed of light in kilometers per second, so instead of 3 × 10⁸ meters per second, I've got 3 × 10⁵ kilometers per second, multiplied by the 0.37 for z. And then if you divide by h0 in its sort of astronomical units, as it were, the 73 kilometers per second per megaparsec, then the distance here will come out directly in megaparsecs. And you see we get now up to 1500 megaparsecs. Okay. So we've come a long way. Okay, we started with the sun being 1 AU away, and then the nearest star being 1 parsec away, and then our own galaxy being like 100 kiloparsecs across, and then the next nearest galaxy being about 1 megaparsec across, and now we're out, well out into the universe at thousands of megaparsecs. So this brings us to trying to explain Hubble's law. So why is it that the galaxies that are further and further away are receding from us at higher and higher velocities? Okay, which is what Hubble's law says. And obviously people puzzled throughout the 20th century and argued vigorously as to why, how you could explain this. And the simplest explanation is that the universe is just uniformly expanding in all directions. Okay, so that's by far the simplest explanation, and often in science the simplest explanation is the best one, and it sort of just naturally explains things. But of course, the fact that the universe is expanding then leads to other very interesting questions. I'll touch on a few here, but you know, if you really want to look into these questions deeply, then you know, we've got a whole third-year module on cosmology which deals with all of these questions in much more detail than I will here, and I'm no cosmologist either. So. But a few common misconceptions. So the galaxies are not sort of rushing through some kind of space, or definitely not some kind of ether, as it were. But it's more sensible to think of space itself expanding. And of course, really, we need to actually think in terms of space-time after Einstein as well, really. But the idea that space itself is expanding and the galaxies go along with that is sort of more like the right idea. Another common misconception coming from Hubble's law, and the fact that here where we are, we look out in all directions, and everything that is things that are further away from us are receding from us at a faster speed. Makes people think that we must be at the center of some universe, it's the center of some sort of explosion or something. But that's also not true, as I shall demonstrate that in a moment. Okay. If you were any other galaxy anywhere else in the universe, you would come to exactly the same conclusion that we have. And a kind of tricky question is, what is the universe expanding into? And here, again, it's much better to think of the universe encapsulating all of sort of space-time, and basically we're not expanding into anything else, at least that we can perceive. So again, it's the whole of space and time is expanding. Okay, so let's just address a few of those points here a little bit to try and explain why an expanding universe explains Hubble's law. So here we're sort of considering the universe as a just so that we can visualize things, just consider it as two-dimensional rather than three-dimensional, or even four-dimensional for a moment. And imagine that we've got like a black rubber sheet here that can expand uniformly in all directions, 2 dimensions, and that we've put some idealized galaxies down here as markers on this coordinate system, if you like. So the coordinate system here is representing the idea that space itself is expanding. Okay. Now, so here we are, and we've got 5 galaxies here. Okay, so with placed regular distances 100 megaparsecs apart. Okay, and this figure B here represents some time interval later when the universe has expanded up by 50%. Okay. So let's for a moment think that we live in galaxy A, and we're observing the universe from there. So if we consider galaxy B here, okay, so galaxy B has moved from 100 parsecs away from us to 150 parsecs away from us in that time interval. But if you now go and look at galaxy C, it started off as 200 megaparsecs away from us, but here it is now 300 megaparsecs away from us. Okay. So the time interval change is the same, okay, but the distance that C has increased away from us in that same time interval is twice what it is for B, which effectively means that C is receding from A at twice the velocity of B. Okay. And the same if you go to D. Okay, D starts off 300 megaparsecs away, but here the distance of D will have changed by, we've gone up to 450 megaparsecs, or the difference will be 150 megaparsecs compared to B. So that's 3 times faster, and it was 3 times further away. So this sort of naturally explains the V is proportional to D type of argument or observation that Hubble made. Okay. And you'd get the same thing if you went off in any different direction. Okay. So galaxy E has also moved 50 megaparsecs further away in the same time interval that B has, so, and they are at the same distance away from A, so therefore you look in any direction, you're going to get the same answer. And if instead we lived in D rather than A, and you went through the same argument again, anyone observing the universe from galaxy D would also come to exactly the same conclusion. So that's the idea that we're not at a special location. And this sort of mind's eye picture explains why a uniformly expanding universe naturally, simply explains Hubble's law. Okay. But of course, it also has some implications. So when did the universe start expanding? What was it like when it started expanding? And how long has it been expanding? So we can do a sort of dimensional argument here, which actually is quite sort of accurate in the answer you get. So if we assume the universe has been expanding at a constant rate, so basically the rate that we see it sort of expanding today, as it were, from where we are, if the universe has always been expanding at that same rate as it is now, then we can use sort of the arguments from Hubble's law really to just make an estimate of the age. Okay. So the time it takes to travel some distance at some speed v is just d over v. Okay. So that's dimensionally what time means, okay, in terms of distance and velocity. Okay. So we can take Hubble's law, okay, and just look at what d over v is in terms of Hubble's law, and it's just 1 over h0. Okay. So this is, I've put an approximation here, so this is more like a dimensional kind of argument. Okay. So it's another way of saying, how long has it been since all the galaxies were very, very close together? Another way of thinking about it. Okay. And that just comes out as 1 over h naught. Okay. And again, you can see this really if you go back and look at the dimensions of h naught. Okay. So it's in units of kilometers per second per megaparsec. But of course, kilometers and megaparsecs are both units of length, and so they cancel out. So h naught has, if you expressed it in SI units, would have units of just per second. So therefore, 1 over h naught has units of seconds or time. So let's do that calculation. Okay. So 1 over h naught is 1 over 73 in these sort of strange units. I've inverted the units here. Okay. So we now just need to put in the appropriate factors to turn that back into just seconds. So we need to multiply by the number of meters in a megaparsec. Okay, we've got megaparsecs here, so that's 3.1 10 to the 22. And then we need to divide by the factor of 1,000 to turn this kilometers into meters, okay, or per kilometers into per meter. And if you work all these numbers out, you get 4 10 to 17 seconds, which is about 13.7 billion years. And this is pretty close to what the latest cosmological theories would have you believe for the age of the universe. Okay. And so this time, 1 over h naught is referred to as the Hubble time, okay, and is, for first order, is a good estimate of the total age of the universe since it started expanding. So, which takes us to what happened at the beginning. So, as I'm sure you're aware, then the idea is that the universe began in some kind of hot big bang, as it's called. Okay, and again, I'm not going to go into much detail here at all, but just to sort of set the scene for the cosmology module in the 3rd year. So the way to think about this is to sort of start winding the clock backwards. Okay, so at the moment, all the galaxies are rushing away from each other. But if we wind time backwards, then they'll all start coming closer and closer together. And so logically, if you keep winding the clock backwards, then all the galaxies will sort of appear to sort of merge into one, and then all the stars will get very, very close together. And then you've got lots and lots of matter all packed into a very small volume of space. And in effect, that brings us back to the idea of a singularity. Okay, so you've got all of the matter of the universe packed into an ever increasingly small volume, and so this was the kind of mental breakthrough, if you like, and mathematical breakthrough that Stephen Hawking made during his PhD, was to think about the very early universe, in a sense, as a black hole with time going in the other direction. Okay, so instead of everything falling into the black hole, it's like everything coming out and starting to sort of expand again. And so that's kind of one way to think about that. Now, there's an awful lot more evidence for the idea that the universe started with a hot Big Bang than just what I've outlined here. And basically, pretty much every test, and this theory, because it's kind of quite startling in a way, and has been severely tested with every possible type of observation that we can think of, and so far it's passed all of those tests. It's not to say there are lots of things we don't understand. In fact, there's even more things we don't understand probably than a few years back. But this concept is still central to all of the theories and all of our understanding of the origins of the universe. Okay, so to bring us back to sort of the galaxies topic that we're looking at in this module, and to sort of tie up a few loose ends here, then the fact that we're now talking about extraordinarily large distances, okay, like thousands of megaparsecs, that has massive implications now for what it is we're looking at when we look at distant galaxies. And this is because of the finite speed of light. Okay? So because these galaxies are so far away, the light traveling from them takes an awfully long time to get here. And what that means is that the time when that light was actually emitted was a long time ago, and it becomes significant compared to the actual age of the universe since the Big Bang itself. Okay? So that this comes back to this idea that we looked at in workshop 4 when we looked at these kind of pictures from the very, very faint galaxies, which are a very long way away. Okay, so these are from galaxies, or the light emitted from these galaxies was emitted a very long time ago. And so we are seeing these galaxies as they appeared when the universe is much younger than it is today. So this is the idea about look-back time. Okay, and of course it's a fantastic tool for us. Okay, if we want to study, what the universe looked like a long time ago, then all we've got to do is keep looking further and further, more and more distant objects, and we're looking further and further back in cosmic time. And that's why the galaxies here in these deep images look so different to the ones that we see today. The universe was a lot smaller, galaxies were packed closer together, and there's lots and lots of interaction. Okay. And so we touched on that in workshop 4, in the whole idea of the evolution of galaxies over cosmic time. And people are now really pushing that to the limit and trying to look for the very first galaxies, okay, and the very first stars. Okay. So again, just to sort of recap the Big Bang, but now going in the correct direction for time, then basically the universe started as just think of it as a hot ball of gas, just pure gas, mostly hydrogen, a little bit of helium, nothing else, pretty much. And it's expanding over time, and because the gas is expanding, space and gas, everything's expanding, it's cooling down. So this ball of gas was cooling and cooling and cooling. And at some point, the gas got cool enough that gravity could really get to work and start to, make patches of gas that were slightly overdense collapse on themselves, and gravity will then collapse them down into the very first stars, and you get a whole bunch of stars and start to form galaxies. So people are looking for those very, very first galaxies and starting to make quite a lot of progress. So in redshift terms, then these first galaxies are actually occurring at redshifts of sort of 6, 7, 8, those kind of things. And the kind of the big radio project that I'm working on, the Square Kilometre Array, will be trying to look even further back to redshifts 10 to 20, looking for these signs of when very first stars started to sort of ionize their surroundings and form H2 regions, and the Square Kilometre Array will hopefully detect and even image those signals as well. Okay, so let's just summarize what we've been learning here. So the more distant a galaxy is, the faster it's receding away from us. That's Hubble's law. The more distant galaxies are, then the greater their look-back time, the longer ago we actually sort of, the light was emitted. But it doesn't mean they're older than us, it means they're much younger than us. The light was emitted when the universe was at an earlier stage. Okay. And the basic idea to explain Hubble's law is that we live in an expanding universe that started with a Big Bang. Okay, so to finish up, if you can use the idea of the finite speed of light, okay, you already looked up how far, you already worked out how far away this galaxy is. So now do the same thing, but work out how long it took the light to travel from that galaxy at a redshift of 0.37, which isn't, you know, I've just been talking about galaxies that are much, much further away than that. But again, don't forget that this is about the biggest redshifts we can use with the simple non-relativistic formula that we're only using in this module. So don't try and do these calculations when z is greater than 1, because you get, well, or even approaching 1, because it won't make any sense. Okay. But so here, for this one, you get a reasonable answer. Okay. So have a look at that. And next week, we'll come back and look at the kind of distribution of galaxies in the universe. What kind of spatial distribution of galaxies do we see out there on these large cosmological scales?